Hello, and welcome to the 10th in a series of films about the standard level organic topic. Here we're going to be looking at a number of other functional groups that contain oxygen. So having introduced the alcohols in the previous film, here we're going to look at the aldehydes, ketones and carboxylic acids. So hopefully by the end of this film you'll know how to spot those three functional groups in the molecule, you'll know what they look like, and you'll be able to name these compounds once again for straight chains up to 6 carbons in length. Okay, so let's start off by looking at aldehydes. Aldehydes have in them, just like all the compounds we're going to look at in this film, a carbon-oxygen double bond. Okay, so here we've got the carbon and the oxygen, and they're joined together by a double bond. This is called a carbonyl group, okay, and it's present in all these compounds we're looking at here in this film. Okay, here's how it's represented on, let me just put that in a different color so we can see it on this diagram. There's that carbon-oxygen double bond, and what we can see here in both of these formulae, or representations of the molecule, is that not only does an aldehyde have a carbon-oxygen double bond, but this carbon that is double bonded to the oxygen also has a hydrogen attached to it. Okay, it doesn't really matter what's on the other bond, but for this molecule to be an aldehyde, it has to not only have carbon-oxygen double bond, but this carbon has to be bonded to a hydrogen. Okay, so the way we write this, if we're writing a structural formula rather than drawing a displayed one, is CHO. Now you might remember in the previous film I was saying that if you've got an alcohol, it ends in COH. You can see that an aldehyde also kind of has COH at the end, but if you write it as COH, you're writing down the formula of an alcohol, or you're looking like you're trying to. Okay, so to distinguish an aldehyde structural formula from an alcohol one, we write CHO at the end instead of COH. How do we name aldehydes? Well, once again, we're using exactly the same prefixes as before to denote how many carbons there are in the chain. So meth, eth, prop, bute, pent, and hex up to 6. Okay, but now we're aldehydes, not alcohols. So we're not ending in ol, we're ending in al. Okay, and here's what the formulas look like. Notice they all end in CHO or CHO. And again, if we want to draw their structures, then it's simply a matter of deciding how many carbons you've got, putting in a double bond oxygen and a hydrogen, and let's just go for butanol, say, then we'd have to have another 3 carbons, and obviously we would do the right thing here and fill in all the hydrogen atoms, not just leave them as blank bonds like I've done there. Okay. I think we've drawn enough of those now for me not to need to draw them all out for you. But let's have a look now at what a ketone is. Okay, now a ketone, like an aldehyde, like we said before, all the molecules in this film have a carbon-oxygen double bond. But what you'll notice with a ketone is that this carbon here, that's double bonded to the oxygen, does not have a hydrogen bonded to it. In fact, it's got carbons both sides. Okay, so in other words, quite similar to an aldehyde, but your carbon-oxygen double bond has to be bonded to, or directly to, 2 carbon atoms. Okay, and the way we draw this, or that's how we draw it. The way we write it in a structural formula is just CO. Okay, so this would be this molecule here. If we just drew it out, it would have a CH3 on the end. This CO means that we've got a carbon-oxygen double bond and then another CH3 group on the end there. Okay, so that's what a ketone is. Very similar to an aldehyde, but very importantly different as well. How do we name ketones? Well, guess what? We've got exactly the same system of prefixes, prop, bute, pentan, hexan, okay? But we can't have ketones with 1 or 2 carbon atoms, because if you think about it, if you've got to have a carbon in both of these positions, then you've got to have at least 3 carbon atoms in a ketone. So the smallest ketone we can have is propanone, and there it is with these things being CH3s, but obviously I'm not drawing the hydrogens, which is very bad indeed. Okay, butanone would have another carbon in. Okay, but you might be thinking now, oh, there's the potential here for structural isomerism, and that's quite right. And that's because once your chain is long enough, your carbon-oxygen double bond could be in various positions in the chain. This is the first time. The first time this is going to happen is when you have 5 carbons, because if you think about it, if you only have 4, and you've got to have the carbon-oxygen double bond not at the end of the chain, because if you did, let's just draw that again, if there were no more carbons here, it would have to be a hydrogen atom here, and now you'd have an aldehyde, which is why you can't have structural isomers of aldehydes if they've got straight chains, because the aldehyde group has to be on the end. Okay, but if you've got different places where you could put this carbon-oxygen double bond, so here it's on the second carbon in the 5 carbon chain, then you're going to have to name the different possibilities differently. So this would be pentan-2-one, okay, and if we put the carbon-oxygen double bond on the 3rd carbon along, then we'd have pentan-3-one. So here the number is denoting where the carbon-oxygen double bond is, and because we've got ketones, I don't think I mentioned this on the previous slide, they all end in -one. Okay, finally for this film, let's have a look at what we mean by a carboxylic acid. Once again, we can see here the presence of this carbon-oxygen double bond. What we can also see is an OH group. But this isn't an alcohol because this OH group is attached to the carbon-oxygen double bond group. Okay, so if you've got a carbon-oxygen double bond with an OH group attached to it, this is now called a carboxylic acid. Okay, so once again in this diagram here, we can see the carbonyl group, that's the carbon-oxygen double bond, and attached to it our OH group. And if we're writing that in a structural formula, we write it as COOH. What you sometimes see is CO2H, but that's not as common as COOH. Okay, so there we are. That's how to spot a carboxylic acid. Let's move on to talking about how we name them. Now, again, you might be thinking about, can I put the carboxylic acid group in different places in the molecule? Well, if you think about that, if you've got your structure and it's got your carbon-oxygen double bond and an OH, then really the only place that group can be is at the end of the chain, because if this has got to be an OH, then it's not a carbon chain. Okay, so we could have chains of various different lengths. Okay, so I've drawn here 4 carbons in my chain. We do include this one when we're naming it. So this is butan, because it's 4 carbons. Oic acid, so all the carboxylic acids end in oic acid. Okay, and I'm not going to draw many of them out because we should be quite used to just extending chains by now. Okay, so that's introduced these groups. As we'll see later, they come into the reactions of alcohol, so it's important to be able to recognize them not only for naming purposes, but we'd also need to be able to draw them as the products of reactions. So hopefully you now know what we mean by an aldehyde, by a ketone and a carboxylic acid, and you can name the first 6 aldehydes, ketones and carboxylic acids. You only have to do this for straight chains. As usual, any questions or comments, please come and see me or post a comment on the YouTube channel.